The last lecture of 6046. We are here today to talk more about cache-oblivious algorithms. Last class we saw several cache-oblivious algorithms, although none of them quite too difficult. Today we will see two difficult cache-oblivious algorithms, a little bit more advanced. I figure we should do something advanced for the last class just to get to some exciting climax. So without further ado, let's get started. Last time we looked at the binary search problem, or we looked at binary search rather, and saw that binary search did not do so well in the cache-oblivious context. And some people asked me after class, is it possible to do binary search well cache-obliviously? And indeed it is, with something called static search trees. So this is really binary search. So the abstract problem is I give you n items, let's say pre-sorted, build some static data structure so that you can search among those n items quickly. And quickly, I claim, means log base b of n. We know that with B trees, so our goal is to get log base b of n. We know that we can achieve that with B trees when we know B. We'd like to do it when we don't know B. And that's what cache-oblivious static search trees achieve. So here's what we're going to do. As you might suspect, we're going to use a tree. So we're going to store our n elements in a complete binary tree. We can't use B trees because we don't know what B is, so we'll use a binary tree. And the key is how we lay out that binary tree. The binary tree will have n nodes, or you can put the data in the leaves, doesn't really matter. So here's our tree. There are the n nodes. And we're storing them, I didn't say, in order. You know, in the usual way. In order in a binary tree, which makes it a binary search tree. So we know how to search in this thing. So search will just start at the root and walk down some root to leaf path. Okay, and at each point you know whether to go left or go right, because things are in order. So we're assuming here we have an ordered universe of keys. So that's easy. We know that will take log n time. The question is how many memory transfers. We'd like a lot of the nodes near the root to be somehow clustered together in one block, but we don't know what the block size is. So what we're going to do is carve the tree in the middle level. We're going to use divide and conquer for our layout of the tree, how we order the nodes in memory. And the divide and conquer is based on cutting in the middle, which is a bit weird. It's not our usual divide and conquer. And we'll see this more than once today. So when you cut in the middle level, if the height of your original tree is log n, roughly, it's maybe log n minus plus 1 or something. But it's roughly log n, then the height of the top half will be log n over 2. And the height of the bottom pieces will be log n over 2. How many nodes will there be in the top tree? N over 2? Not quite. 2 to the log n over 2, square root of n. Okay, so it'll be about root n nodes up here, and therefore there'll be about root n subtrees down here, one for each, or a couple for each leaf. Okay, so we have these subtrees of root n, and there are about root n of them. Okay, this is how we're carving our tree. Now we're going to recurse on each of the pieces. I'd like to redraw this slightly, sorry. Just to make it a little bit clearer. These triangles are really trees, and they're connected via edges to this tree up here. So what we're really doing is carving in the middle level of edges in the tree. And if n is not exactly a power of 2 or power of 2, you have to round your level by taking floors or ceilings, but you cut roughly in the middle level of edges. There's a lot of edges here. You conceptually slice there, that gives you a top tree and a bottom tree, and several bottom trees, each of size roughly root n. Okay, and then we're going to recursively lay out these root n plus 1 subtrees, and then concatenate. So this is the idea of a recursive layout. We saw recursive layouts with matrices last time. This is doing the same thing for a tree. So I want to recursively lay out the top tree. So here's the top tree. And I imagine it being somehow squashed down into a linear array recursively. And then I do the same thing for each of the bottom trees. So here are all the bottom trees. And I squash each of them down into some linear order. And then I concatenate those linear orders. That's the linear order of this tree. And you need a base case. In the base case, a single node is stored in the only order of a single node there is. Okay, so that's a recursive layout of a binary search tree. Turns out this works really well. And let's quickly do a little example, just so it's completely clear what this layout is, because it's a bit bizarre maybe the first time you see it. So let me draw my favorite picture. So here's a tree of height 4 or 3, depending on how you count. We divide in the middle level, and we say, okay, that's the top tree, and then these are the bottom trees. So there's 4 bottom trees. So there are 4 children hanging off the root tree. They each have the same size in this case. They should all roughly be the same size. And first we lay out the top thing, where we divide in the middle level. We say, okay, this comes first, and then the bottom subtrees come next, 2 and 3. So I'm writing down the order in which these nodes are stored in an array. And then we visit this tree, so we get 4, 5, 6. Then we visit this one, so we get 7, 8, 9. And then this subtree, 10, 11, 12. And then the last subtree. So that's the order in which you store these 15 nodes. And you can build that up recursively. Okay, so the structure is fairly simple. It's just a binary search tree which we know and love, but stored in this funny order. This is not depth first search order or level order. There are lots of natural things you might try, none of which work in cache oblivious context. This is pretty much the only thing that works. And the intuition is, well, we're trying to mimic all kinds of B trees. So if you want a binary tree, well, that's the original tree. It doesn't matter how you store things. If you want a tree where the branching factor is 4, then here it is. These blocks give you a branching factor of 4. If we had more leaves down here, there would be 4 children hanging off of that node. And these are all clustered together consecutively in memory. So if your block size happens to be 3, then this is a perfect way to store things for a block size of 3. If your block size happens to be probably 7, it's probably even bigger, 15, right? If we count the number the number of nodes in here is 15. If your block size happens to be 15, then this recursion will give you a perfect blocking in terms of 15. Okay, and in general, it's actually mimicking block sizes of 2 to the 2 to the k minus 1. I think powers of 2. Okay, that's the intuition. Let me give you the formal analysis, which should make it clearer. So we claim that there are order log base b of n memory transfers. That's what we want to prove, no matter what b is. So here's what we're going to do. You may recall last time when we analyzed divide and conquer algorithms, we wrote a recurrence, and then the base case was the key. here, in fact, we're only going to think about the base case in a certain sense. We don't have really a recursion in the algorithm. The algorithm is just walking down some route to leave path. We only have a recursion in the definition of the layout. So we can be a little bit more flexible. We don't have to look at a recurrence. We're just going to think about the base case. I want to imagine you start with this big triangle. Then you cut it in the middle, you get smaller triangles. Imagine the point at which you keep recursively cutting. So imagine this process. Your big triangles halve in height each time. They're getting smaller and smaller. Stop cutting at the point where a triangle fits in a block. Okay, and look at that time. Okay, the recursion actually goes all the way, but in the analysis, let's think about the point where the chunk fits in a block, where one of these triangles, one of these boxes fits in a block. So I'm going to call this a recursive level. So I'm imagining expanding all of the recursions in parallel. This is some level of detail, some level of refinement of the trees, at which the tree you're looking at, the triangle, has size. In other words, the number of nodes in that triangle is less than or equal to b. Okay, so let me draw a picture. So I want to draw sort of this picture, but where instead of nodes, I have little triangles of size at most b. So the picture looks something like this. We have a little triangle of size at most b. It has a bunch of children, which are subtrees of size at most b, the same size. And then these are in a chunk. And then we have other chunks that look like that in the recursion, potentially. Okay, so I haven't drawn everything. There'd be a whole bunch of something between b and b squared, in fact, subtrees, other squares of this size. So here I had to refine the entire tree here. Then I refined each of the subtrees here and here at these levels. And then it turned out after these two recursive levels, everything fits in a block. Everything has the same size. So at some point, they will all fit within a block. Now, they might actually be quite a bit smaller than a block. How small? So what I'm doing is cutting the number of levels in half at each point. And I stop when the height of one of these trees is essentially at most log b. Okay, because that's when the number of nodes in there will be b, roughly. So how small could the height be? If I keep dividing in half and stopping when it's at most log b. Log b over 2. So it's at most log b, it's at least a half log b. Therefore, the number of nodes in here could be between square root of b and b. So this could be a lot smaller, less than a constant fraction of a block. I claim that it doesn't matter. It's okay. This could be as small as square root of b. I'm not even going to write that it could be as small as square root of b, because that doesn't play a role in the analysis. It's a worry, but it's okay. Essentially, because our bound only involves log b, it doesn't involve b. So here's what we do. We know that each of the height of one of these triangles, of size at most b, is at least a half log b. And therefore, if you look at a search path, so when we do a search in this tree, we're going to start up here, and I'm going to mess up the diagram now. We follow some path. Maybe I should have drawn it going down here. We visit through some of these triangles, but it's a root to node path in the tree. So how many of the triangles could it visit? Well, the height of the tree divided by the height of one of the triangles. So this visits at most log n over half log b triangles. which looks good. This is log base b of n, modulo a factor of 2. Now, what we worry about is how many blocks does a triangle occupy? One of these triangles should fit in a block, but we know by the recursive layout it is stored in a consecutive region in memory. So how many blocks could it occupy? 2. Because of alignment, it might not be, it might fall across the boundary of a block, but at most one boundary. So it fits in 2 blocks. So each triangle fits, or it fits in 1 block, but is in at most 2 blocks, memory blocks, size B, depending on alignment. So the number of memory transfers, in other words, the number of blocks we read, because all we're doing here is reading in a search, is at most 2 blocks per triangle. There are this many triangles, so it's at most 4 log base b of n, okay, which is order log base b of n. And there are papers about decreasing this constant 4 with more sophisticated data structures. You can get it down to a little bit less than 2, I think. But there you go. So not quite as good as B trees in terms of the constant, but pretty good. And what's neat is that this data structure works for all B at the same time. This analysis applies for all B. So if you have a multi-level memory hierarchy, no problem. Any questions about this data structure? This is already pretty sophisticated, but we're going to get even more sophisticated. Next. Okay. Good, no questions. It's either perfectly clear or a little bit difficult, or both. So now I debated with myself for some time what exactly I would cover next. There are 2 natural things I could cover, both of which are complicated. One is, my first result in cache oblivious world is making this data structure dynamic. So there's a dynamic B tree. It's cache oblivious, so it works for all values of B. And it gets log base B of n, insert, delete, and search. So this just gets search in log base B of n. That data structure, our first paper was damn complicated, and then it got simplified. It's now not too hard, but it takes like a couple of lectures in an advanced algorithms class to teach it. So I'm not going to do that one. But there you go. It exists. Instead, we're going to cover our favorite problem, sorting, in the cache oblivious context. And this is quite complicated, more than you would expect. Okay, much more complicated than it is in a multi-threaded setting, to get the right answer anyway. Maybe to get the best answer in the multi-threaded setting is also complicated. The version we got last week was pretty easy. But before I go to cache oblivious sorting, let me talk about cache aware sorting, because we need to know what bound we're aiming for. And just to warn you, I may not get to the full analysis of the full cache oblivious sorting, but I want to give you an idea of what goes into it, because it's pretty cool, I think. A lot of ideas. So how might you sort? So cache aware, we assume we can do everything. Basically, this means we have B trees. That's the only other structure we know. How would you sort n numbers, given that that's the only data structure you have? Right, just add them into the B tree and then do an in-order traversal. That's one way to sort. Perfectly reasonable. We'll call it repeated insertion into a B tree. Okay, we know in the usual setting, BST sort, where you use a balanced binary search tree like red-black trees, that takes n log n time, log n per operation. And that's an optimal sorting algorithm in the comparison model. Only thinking about comparison model here. So how many memory transfers does this data structure take? Sorry, this algorithm for sorting. Number of memory transfers is a function of n and b and m is this is easy. and insertions. Okay, you have to think about in-order traversal. You have to remember back to your analysis of B trees. But this is not too hard. How long does the insertion take? The n insertions. N log base B of n. How long does the traversal take? Less time. If you think about it, you can get away with n over b memory transfers, so quite a bit less than this. This is bigger than n, which is actually pretty bad. N memory transfers means essentially you're doing random access, visiting every element in some random order. It's even worse. There's even a log factor. Now, the log factor goes down by this log b factor, but this is actually a really bad sorting bound. So unlike normal algorithms where using a search tree is a good way to sort, in cache-oblivious or cache-aware sorting, it's really, really bad. So what's another natural algorithm you might try, given what we know, for sorting? And let's even cache-oblivious. I mean, we have all the algorithms we've seen are cache-oblivious. So what's a good one to try? Merge sort, right? We did merge sort with in multi-threaded algorithms. Let's try merge sort. It's a good divide and conquer thing. So I'm going to call it binary merge sort because it splits the array into two pieces and recurses on the two pieces. So you get a binary recursion tree. So let's analyze it. It's the number of memory transfers on n elements. So, I mean, it has a pretty good recursive layout, right? The two subarrays that we get when we partition our array are consecutive. So we're recursing on this, recursing on this. So it's a nice cache-oblivious layout. And this is even for cache-aware. This is a pretty good algorithm. A lot better than this one, as we'll see. But what is the recurrence we get? So here we have to go back to last lecture when we were thinking about recurrences for recursive cache-oblivious algorithms. I mean, the first part should be pretty easy. There's an O.
The first part.
Well, okay, let's put the O at the end, the divide and the conquer part at the end. The recursion is 2mt of n over 2. Good. Right, that's just like the merge sort recurrence. And it's the additive term that you're thinking about. Okay, so normally we would pay an additive term, a linear additive term here, order n, because merging takes order n time. Now we're merging, which is 3 parallel scans, the 2 inputs and the output. Okay, they're not quite parallelly interleaved. They're a bit funnily interleaved, but as long as your cache stores at least 3 blocks, this is also linear time in this setting, which means you visit each block a constant number of times. Okay, that's the recurrence. Now we also need a base case, of course. We've seen 2 base cases, one mt of b and the other mt of whatever fits in cache. So let's look at that one because it's better. So for some constant c, if I have an array of size m, this fits in cache. Actually, probably c is 1 here, but I'll just be careful. For some constant, this fits in cache. Problem of this size fits in cache. And in that case, the number of memory transfers is, anyone remember? We've used this base case more than once before. Do you remember? Sorry? Cm over b. I've got a big O, so like m over b. Order m over b because this is the size of the data. So the number, I mean, just to read it all in takes m over b. Once it's in cache, it doesn't really matter what I do as long as I use linear space. So for the right constant here, as long as I use linear space in that algorithm, I'll stay in cache and therefore not have to write anything out until the very end, and I spend m over b to write it out. Okay, so I can't really spend more than m over b, almost no matter what algorithm I have. as long as it uses linear space. So this is a base case that's useful in pretty much any algorithm. Okay, that's a recurrence. Now we just have to solve it. Okay. Let's see how good binary merge sort is. Okay, and again, I'm going to just give the intuition behind the solution to this recurrence, and I won't use the substitution method to prove it formally. But this one's actually pretty simple. So we have at the top, actually I'm going to write it over here, otherwise I won't be able to see. So at the top of the recursion, we have n over b cost. I'll ignore the constants. There's probably also an additive one, which I'm ignoring here. Then we split into two problems of half the size, so we get a half n over b and a half n over b. Okay, usually this was n, half n, half n. You should remember this from lecture 1. So the total on this level is n over b. The total on this level is n over b. And you can prove by induction that every level is n over b. The question is, how many levels are there? Well, at the bottom, so dot, dot, dot. At the bottom of this recursion tree, we should get something of size m. And then we're paying m over b. Actually, here, we're paying m over b. So it's a good thing those match. They should. So here we have a bunch of leaves, all of size m over b. You can also compute the number of leaves here is n over m. Okay, if you want to be extra sure, you should always check the leaf level. It's a good idea. So we have n over m leaves, each costing m over b. This is an m. So this is n over b also. So every level here is n over b, memory transfers. And the number of levels is one. N over b? Log n over b. Yep, that's right. Just didn't hear it right. Okay, we're starting at n. We're getting down to m. So you can think of it as log n, the whole tree, whole binary tree, minus the subtrees log m. And that's the same as log n over m. Okay, or however you want to think about it. The point is this is a log base 2. That's where we're not doing so great. But this is actually a pretty good algorithm. So let me write the solution over here. So number of memory transfers on n items is going to be the number of levels times the cost at each level. So this is n over b times log base 2 of n over m, which is a lot better than repeated insertion into a B tree. Here, we were getting n times log n over log b. Okay, so n log n over log b. We're getting a log b savings over not proving anything. And here, we're getting a factor of b savings, n log n over b. In fact, we even made it a little bit smaller by dividing this n by m. That doesn't matter too much, but this dividing by b is a big win. Okay, so we're almost there. This is almost an optimal algorithm. It's even cache oblivious, which is pretty cool. And that extra little step, which is that you should be able to get another log b factor improvement. I want to combine these two ideas. I want to keep this factor b improvement over n log n, and I want to keep this factor log b improvement over n log n and get them together. So first, before we do that cache obliviously, let's do it cache aware. So this is the third cache-aware algorithm. This one was also cache-oblivious. So how should I modify merge sort in order to do better? I mean, I have this log base 2, and I want a log base b, more or less. So how would I do that with merge sort? Yeah. Split into b subarrays. Yeah. So instead of doing binary merge sort, this is what I was hinting at here, instead of splitting into two pieces and recursing on the two pieces and then merging them, I could split potentially into more pieces. Okay. And to do that, I'm going to use my cache. So the idea is b pieces. That's not actually the best thing to do, although b pieces does work. And it's what I was hinting at because I was saying I want a log b. It's actually not quite log b. It's log m over b. Okay, but let's see. So what is the most pieces I could split into? Right? Well, I need to still be able, I could split into n pieces. That would be good, wouldn't it? And only one recursive level. I can't split into n pieces. Why? What happens wrong when I split into n pieces? That would be the ultimate. You can't merge, exactly. So if I have n pieces, I can't merge in cache. I mean, so in order to merge in cache, what I need is to be able to store an entire block from each of the lists that I'm merging. If I can store an entire block in cache for each of the lists, then it's a bunch of parallel scans. So this is like testing the limit of parallel scanning technology. If you have k parallel scans and you can fit k blocks in cache, then all is well, because you can scan through each of those k arrays and have one block from each of the k arrays in cache at the same time. So that's the idea. Now, how many blocks can I fit in cache? M over B. That's the biggest I could do, so this will give the best running time among these kinds of merge sort algorithms. This is an M over B way merge sort. Okay, so now we get somewhat better recurrence. We split into M over B subproblems now, each of size, well, it's n divided by M over B, without thinking. And the claim is that the merge time is still linear, because we have barely enough. Okay, maybe I should describe this algorithm. So we divide, because we've never really done non-binary merge sort. We divide into M over B equal size subarrays instead of 2. Here we are clearly doing a cache-aware algorithm. We're assuming we know what M over B is. So then we recursively sort each subarray. And then we conquer, we merge. And the reason merge works is because we can afford one block in cache. So let's call it one cache block per subarray. Okay, actually, if you're careful, you also need one block for the output of the merged array before you write it out. So it should be M over B minus 1. But let's ignore some additive constants. Okay, so this is the recurrence we get. The base case is the same. And what improves here? I mean, the per level cost doesn't change, I claim, because at the top we get N over B just as before. Then we split into M over B subproblems, each of which costs a 1 over M over B factor times N over B. Okay, so you add all those up, you still get N over B. Because we're not decreasing the number of elements, we're just splitting them. There's now M over B subproblems, each of 1 over M over B the size. So just like before, each level will sum to N over B. What changes is the number of levels, because now we have bigger branching factor. Instead of log base 2, it's now log base the branching factor. So the height of this tree is log base M over B of N over M, I believe. Sure, that agrees with me. Yeah. Okay, and if you're careful, this counts not quite the number of levels, but the number of levels plus 1, or minus 1. So I'm going to add on a plus 1 here. And the reason why is this is not quite the bound that I want. Let me rewrite it a little bit. So we have log base M over B. What I really want actually is N over B. I claim that these are the same because we have minus that's good. Okay, this should come as rather mysterious, but it's because I know what the sorting bound should be that I'm doing this arithmetic. So I'm taking log base m over b of n over m. I'm not changing the base of the log. I'm just saying, well, n over m, that is n over b divided by m over b, because then the b's cancel and the m goes in the bottom. So if I do that in the logs, I get log of n over b minus log of m over b, minus because I'm dividing. Okay, now log base m over b of m over b is 1. So these cancel. And I get log base m over b n over b, which is what I was aiming for. Why? Because that's the right bound. That's how it's normally written. And it's what we will be trying to get cache obliviously. So that's the height of the search tree. And at each level, we're paying n over b memory transfers. So the overall number of memory transfers for this m over b way merge sort is the sorting bound. This is, I'll put it in a box. How's that? This is the sorting bound. And it's very special because it is the optimal number of memory transfers for sorting n items, cache aware. This has been known since like 1983. Okay, this is the best thing to do. It's a really weird bound, but if you ignore all the divided by b's, it's sort of like n divided by n times log base m of n. So that's a little bit more reasonable, but there's lots of divided by b's. It's the number of blocks in the input times log base the number of blocks in the cache of the number of blocks in the input. That's a little bit more intuitive. That is the bound, and that's what we're aiming for. So this algorithm crucially assumed that we knew what m over b was. Now we're going to try and do it without knowing m over b. Do it cache obliviously, and that is a result of only a few years ago. Are you ready? Everything clear so far? It's a pretty natural algorithm. We're going to try to mimic it, essentially, and do a merge sort, but not m over b way merge sort because we don't know how. We're going to try and do essentially a square root of n way merge sort. That's kind of, if you play around, that's the natural thing to do. The tricky part is that it's hard to merge square root of n lists at the same time in a cache-efficient way. We know that if square root of n is bigger than m over b, you're hosed if you just do a straightforward merge. So we need a fancy merge. We're going to do a divide and conquer merge. It's a lot like the multi-threaded algorithms of last week. Try and do a divide and conquer merge so that no matter how many lists are merging, as long as it's less than square root of n, or actually cubed root of n, we can do it cache efficiently. Okay, so we'll do this. We need a bit of setup. But that's where we're going. Cache oblivious sorting. So we want to get the sorting bound. And, yeah, fine. It turns out, to do cache oblivious sorting, you need an assumption about the cache size. This is kind of annoying because we said, well, a cache oblivious algorithm should work for all values of b and all values of m. But you can actually prove you need an additional assumption in order to get this bound cache obliviously. That's a result of like last year by Garrett Brodel. So, and the assumption is, but the assumption is fairly weak. That's the good news. Okay, we've actually made an assumption several times. We said, well, assuming the cache can store at least 3 blocks, or assuming the cache can store at least 4 blocks. Yeah, it's reasonable to say the cache can store at least 4 blocks, or at least any constant number of blocks. This says that the number of blocks that your cache can store is at least b to the epsilon blocks. This is saying your cache isn't like really narrow. It's about as tall as it is wide. This actually gives you a lot of slop. And we're going to use a simple version of this assumption that m is at least b squared. Okay, this is pretty natural. It's saying that your cache is at least as tall as it is wide, where these are the blocks. Okay, the number of blocks is at least the size of a block. That's a pretty reasonable assumption, and if you look at caches these days, they all satisfy this, at least for some epsilon. Pretty much universally, m is at least b squared or so. Okay? And in fact, if you think from our speed of light arguments from last time, b squared or b cubed is actually the right thing to do. As you go out, I guess in 3D, b squared would be the surface area of the sphere out there. Okay? So this is actually the natural thing of how much space you should have at a particular distance. Assuming we live in a constant dimensional space, that assumption will be true. This even allows going up to 42 dimensions or whatever. Okay, so pretty reasonable assumption. Good. Now we're going to achieve this bound. And what we're going to try to do is use an n to the epsilon way merge sort for some epsilon. And if we assume that m is at least b squared, the epsilon will be 1/3, it turns out. So we're going to do cubed root of n way merge sort. I'll start by giving you and analyzing the sorting algorithm, assuming that we know how to do merge in a particular bound. Okay, then we'll do the merge. The merge is the hard part. Okay. So the merge, I'm going to give you the black box, first of all. What does merge do? It's called, the k-way merger is called a k-funnel, just because it looks like a funnel, as you'll see. So a k-funnel is a data structure, or as an algorithm, let's say, though it looks like a data structure. And it merges k sorted lists. So supposing you already have k lists, and they're sorted, and assuming that the lists are relatively long, so we need some additional assumptions for this black box to work, and we'll be able to get them as we sort. We want the total size of those lists. If you add up all the elements in all the lists, it should have size at least k cubed. That's the assumption. Then it merges these lists using essentially the sorting bound. Actually, I should really say theta k cubed. I also don't want it to be too much bigger than k cubed. Sorry about that. So the number of memory transfers that this funnel merger uses is the sorting bound on k cubed, so k cubed over b log base m over b of k cubed over b, plus another k memory transfers. Now, k memory transfers is pretty reasonable. You've got to at least start reading each list. So you've got to pay one memory transfer per list. Okay, but our challenge in some sense will be getting rid of this plus k. This is how fast we can merge. We'll do that after. Now, assuming we have this, let me tell you how to sort. This is, naturally enough, called funnel sort. But in a certain sense, it's really n cube root of n way merge sort. Okay, but we'll analyze it using this. Okay, so funnel sort, we're going to define k to be n to the 1/3 and apply this merger. So what do? It's just like here. We're going to divide our array into n to the 1/3. I mean, they should be consecutive subarrays. I'll call them segments of the array. Okay, for cache oblivious, it's really crucial how these things are laid out. We're going to cut and get consecutive chunks of the array, n to the 1/3 of them. Then I'm going to recursively sort them, and then I'm going to merge. Okay, and I'm going to merge using the k funnel, the n to the 1/3 funnel. Because now this is where, why do I use 1/3? Well, because of this 3. Okay, in order to use the n to the 1/3 funnel, I need to guarantee that the total number of elements I'm merging is at least the cube of this number, k cubed. The cube of this number is n. That's exactly how many elements I have in total. Okay, so this is exactly when I can apply the funnel. It's going to require that I have at least k cubed elements, so then I can only use an n to the 1/3 funnel. I mean, if it didn't have this requirement, I could just say, well, I have n lists, each of size 1. Okay, that's clearly not going to work very well for a merger. I mean, intuitively, because this plus k will kill you. That would be a plus n, which is way too big. But we can use an n to 1/3 funnel, and this is how we would sort. So let's analyze this algorithm. Hopefully, it will give the sorting bound, if I did everything correctly. Okay, the only thing, this is pretty easy. The only thing that makes this messy is I have to write the sorting bound over and over. Okay, this is the cost of the merge. So that's at the root. But k cubed in this case is n. So at the root of the recursion, let me write the recurrence first, sorry. So we have memory transfers on n elements is n to the 1/3, 1/3? Get this right, yeah, n to the 1/3 recursions, each of size n to the 2/3. Okay, plus this time, except k cubed is n. So this is plus n over b log base m over b of n over b plus cube root of n. Is this additive plus k term. Okay, so that's my recurrence. The base case will be the usual. Mt is some constant times m is order m over b. So we sort of know what we should get here. Well, not really. So in all the previous recurrences, we had the same cost at every level, and that's where we got our log factor. Now we already have a log factor, so we better not get another one. Right? This is the bound we want to prove. So, yeah. Let me cheat here for a second. All right, indeed. You may already be wondering, this n to the 1/3 seems rather large. If it's bigger than this, we're already in trouble at the very top level of the recursion. So I claim that that's okay. Let's look at n to the 1/3. Okay, I know there's a base case here which covers all values of n that are at most some constant times m. So if I'm in this case, I know that n is at least as big as the cache up to some constant. Okay, now the cache is at least b squared, we've assumed. And you can do this with b to the 1 plus epsilon if you're more careful. So n is at least b squared. Okay. And then I always have trouble with these. So this means that n divided by b is omega root n. Okay, there's many things you could say here, and only one of them is right. So why? Because so this says that square root of n is at least b. And so n divided by b is at most n divided by square root of n. So that's at least square root of n. Okay, if you check that all out. I'm going to go through this arithmetic relatively quickly because it's tedious but necessary. Okay, square root of n is strictly bigger than cube root of n. Okay, so that means that n over b is strictly bigger than n to the 1/3. Here we have n over b times something that's bigger than 1. So this term definitely dominates this term in this case. As long as I'm not in the base case, I know n is at least order m, this term disappears from my recurrence. Okay, so good. That was a bit close. Now, what we want to get is this running time overall. So the recursive cost better be small, better be less than a constant factor increase over this. So let's write the recurrence. So we get n over b log base m over b, n over b at the root. Then we split into a lot of subproblems, n to the 1/3 subproblems here. And each one costs essentially this, but with n replaced by n to the 2/3. Okay, so n to the 2/3 log base m over b, oops, I forgot to divide it by b out here, of n to the 2/3 divided by b. That's the cost of one of these nodes. There's a bunch of them, n to the 1/3 of them. What do they add up to? Well, there's n to the 1/3 and there's an n to the 2/3 here. That multiplies out to n. So we get n over b. This looks bad. This looks the same. And we don't want to lose another log factor. But the good news is we have a 2/3 in here. Okay, this is what we get in total at this level. Looks like the sorting bound, but in the log, there's still a 2/3. Now, a power of 2/3 in a log comes out as a multiple of 2/3. So this is, in fact, 2/3 times n over b log base m over b of n over b, the sorting bound. So this is 2/3 of the sorting bound. And this is the sorting bound, 1 times the sorting bound. So it's going down geometrically. Yay! Okay, I'm not going to prove it, but it's true. This went down by a factor of 2/3. The next one will also go down by a factor of 2/3 by induction. Okay, if you prove it at one level, it should be true. It should be true at all of them. And I'm going to skip the details there. So we can check the leaf level just to make sure. That's always a good sanity check. At the leaves, we know our cost is m over b. Okay, and how many leaves are there? Just like before, in some sense, we have n over m leaves. Okay, so in fact, the total cost at the bottom is n over b. And it turns out that's what you would get. So you essentially, it looks funny, because you think that this would actually be smaller than this at some intuitive level. It's not. In fact, what's happening is you have this n over b times this log thing. Whatever the log thing is, we don't care too much. Let's just call it log. What you're taking at the next level is 2/3 times that log. Then at the next level, it's 4/9 times that log, and so on. So it's geometrically decreasing until the log gets down to 1. And then you stop the recursion. And that's why you get n over b here with no log. So what you're doing is decreasing the log, not the n over b stuff. The 2/3 should really be over here. In fact, the number of levels here is log log n. It's the number of times you have to divide a log by 3/2 before you get down to 1. Okay, so we don't actually need that. We don't care how many levels there are because it's geometrically decreasing. Could be infinitely many levels. It's geometrically decreasing. And we get this as our running time. MT of n is the sorting bound. For funnel sort. So this is great. As long as we can get a funnel that merges this quickly, we get a sorting algorithm that sorts as fast as it possibly can. Didn't write that, but on the board, this is asymptotically optimal. Even if you knew what B and M were, this is the best you could hope to do. And here we're doing it no matter what B and M are. Good. Are you ready for the funnel? The funnel will be another recursion. So this is a recursive algorithm in a recursive algorithm. It's another divide and conquer, kind of like the static search tree we saw at the beginning of this lecture. So these all tie together. All right, the K funnel. So I'm calling it K funnel because I want to think of it at some recursive level, not just n to the 1/3. Okay, we're going to recursively use, in fact, the square root of K funnel. So and I need to achieve that bound. So the recursion is like the static search tree, and a little bit hard to draw on one board, but here we go. So we have a square root of K funnel recursively. We have a buffer up here. This is called the output buffer. And it has size k cubed. And just for kicks, let's suppose it's been filled up a little bit. Then we have some more buffers. and let's suppose they've been filled up by different amounts. And each of these has size k to the 3/2, of course. And these are called buffers, let's say, or the intermediate buffers. And then hanging off of them, we have more funnels. Square root of k funnel here, and a square root of k funnel here. One for each buffer, one for each child of this funnel. Okay. And then, hanging off of these funnels are the input arrays. Okay, I'm not going to draw all k of them, but there are k input arrays, input lists, let's call them, down at the bottom. Okay, so the idea is we're going to merge bottom up in this picture. We start with our k input arrays of total size at least k cubed. That's what we're assuming we have up here. We're clustering them into groups of size square root of k, so square root of k groups. Throw each of them into a square root of k funnel. That recursively merges those square root of k lists. The output of those funnels we're putting into a buffer to sort of accumulate what the answer should be. These buffers have size exactly k to the 3/2, which might not be perfect because we know that on average there should be k to the 3/2 elements in each of these because there's k cubed total and there's square root of k groups. So it should be k cubed divided by square root of k, which is k to the 3/2 on average. But some of these will be bigger, some of them will be smaller. I've drawn it here. Some of them have emptied a bit more, depending on how you merge things. But on average, these will all fill at the same time, and then we plug them into a square root of k funnel. And then we get the output of size k cubed. So that is roughly what we should have happen. Okay, but in fact, some of these might fill first, and you have to do some merging in order to empty the buffer and make room for more stuff coming up. That's the picture. Now, before I actually tell you what the algorithm is, or analyze the algorithm, let's first just think about space, the very simple warm-up analysis. So let's look at the space, excluding the inputs and outputs, those buffers. Okay, why do I want to exclude input and output buffers? Well, because I only want to count each buffer once. And this buffer is actually the input to this one and the output to this one. So in order to recursively count all the buffers exactly once, I'm only going to count these middle buffers. And then separately, I have to think of the overall output and input buffers. But those are sort of given. I mean, I need k cubed for the output. I need k cubed for the input. So ignore those overall. And then if I count the middle buffers recursively, I'll get all the buffers. So then we get a very simple recurrence for space. S of k is roughly square root of k plus 1 times s of square root of k plus order k squared. K squared because we have square root of k of these buffers, each of size k to the 3/2. Work that out. Does that sound right? Sounds an awful lot like k cubed, but maybe, all right. Oh, no, that's right. It's k to the 3/2 times square root of k, which is k to the 3/2 plus a half, which is k to the 4/2, which is k squared. Whew, okay, good. I'm just bad with my arithmetic here. Okay, so k squared, total buffering here. You add them up for each level, each recursion. And the plus 1 here is to take into account the top guy. There's square root of k bottom guy, so it's square root of k plus 1. If this were, well, let me just draw the recurrence tree. There's many ways you could solve this recurrence. A natural one is instead of looking at k, you look at log k, because here log k is getting divided by 2. I'm just going to draw the recursion tree so you can see the intuition. But if you're going to solve it, you should probably take logs, substitute by logs. So we have square root of k plus 1 branching factor, And then the problem is size squared of k, so this is going to be k, I believe, for each of these. So square root of k squared is the cost at these levels. And you keep going. And I don't particularly care what the bottom looks like, because at the top we have k squared. Then we have k times root k plus 1 cost at the next level. This is k to the 3/2 plus k. Okay, so we go from k squared to k to the 3/2 plus k. This is a super geometric, it's like an exponential geometric decrease. This is decreasing really fast. So it's order k squared. That's my hand-waving argument. Okay, so the cost is basically the size of the buffers at the top level, the total space. We're going to need this. It's actually theta k squared because I have a plus theta k squared here. We're going to need this in order to analyze the time. That's why I mention it. It's not just a good feeling that the space is not too big. In fact, the funnel is a lot smaller than the total input size. Input size is k cubed. But that's not so crucial. What's crucial is it's k squared, and we'll use that in the analysis. Okay, naturally, this thing is laid out recursively. You recursively store the funnel, top funnel. Then, for example, you write out each buffer as a consecutive array in this case. There's no recursion there. Just write them all out one by one. Don't interleave them or anything. Store them in order. And then you write out recursively these funnels, the bottom funnels. Okay, any way you do it recursively, as long as each funnel remains a consecutive chunk of memory, each buffer remains a consecutive chunk of memory, the time analysis that we're about to do will work. Okay, let me actually give you the algorithm that we're analyzing. In order to make the funnel go, what we do is say, so initially all the buffers are empty, everything is at the bottom. And what we're going to do is say, fill the root buffer, fill this one. And that's a recursive algorithm, which I'll define in a second, how to fill a buffer. Once it's filled, that means everything has been pulled up and then it's merged. Okay, so that's how we get started. So merge means, the merge algorithm is fill the topmost buffer, the topmost output buffer. Okay, and now here's how you fill a buffer. So in general, if you expand out this recursion all the way, in the base case I didn't mention, you sort of get a little node there. So if you look at an arbitrary buffer in this picture that you want to fill, so this one's empty and you want to fill it, then immediately below it will be a vertex who has two children, two other buffers. Okay, maybe they look like this. You have no idea how big they are, except they're the same size. They could be a lot smaller than this one, a lot bigger. We don't know. But in the end, you do get a binary structure out of this, just like we did with the binary search tree at the beginning. Okay, so how do we fill this buffer? Well, we just merge these two child buffers as long as we can. So we merge the two children buffers. As long as they're both non-empty. So in general, the invariant will be that this buffer, let me write down the sentence. As long as a buffer is non-empty, or whatever is in that buffer and hasn't been used already, it's a prefix of the merged output of the entire subtree beneath it. Okay? So this is a partially merged subsequence of everything down here. This is a partially merged subsequence of everything down here. I can just merge element by element off the top. And that will give me outputs to put there, until one of them gets emptied. And we have no idea which one will empty first, because it depends on the order. Okay, whenever one of them empties, we recursively fill it. And that's it. That's the algorithm. Whenever one empties, we recursively fill it. And at the base case, at the leaves, there's sort of nothing to do. At the leaf, you just directly read from an input list. So right at the very bottom, if you have some node here that's trying to merge between these two, that's just a straightforward merge between two lists. We know how to do that with two parallel scans. So in fact, we can merge the entire thing here and just spit it out to the buffer. Well, it depends how big the buffer is. We can only merge it until the buffer fills. Whenever a buffer is full, we stop and we pop up the recursive layers. Okay, so we keep doing this merge until the buffer we're trying to fill fills, then we stop, pop up. Okay, that's the algorithm for merging. Now we just have to analyze the algorithm. It's actually not too hard, but it's pretty clever analysis. And to top it off, it's an amortization, your favorite. Okay, so we get one last practice at amortized analysis in the context of cache-oblivious algorithms. So this is going to be a bit sophisticated. We're going to combine all the ideas we've seen. And the main analysis idea we've seen is that we're doing this recursion in the construction. And if we imagine we take our k-funnel, we split it in the middle level, make a whole bunch of square root of k-funnels, and so on, and then we cut those in the middle level, get fourth root of k-funnels, and so on and so on. At some point, the funnel we look at fits in cache. Okay, before we said it fits in a block. Now we're going to say at some point, one of these funnels will fit in cache. Each of the funnels at that recursive level of detail will fit in cache. We're going to analyze that level. Call that level J. So consider the first recursive level detail, and I'll call it J, at which every J funnel we have fits. Let's say it doesn't. Not only does it fit in cache, but 4 of them fit in cache. It fits in 1/4 of the cache. Okay, we need to leave some cache extra for doing other things. But I want to make sure that a J funnel fits. Okay, now what does that mean? Well, we've analyzed space. We know that the space of a J funnel is about J squared, some constant times J squared. Call it C times J squared. Okay, so this is saying that C times J squared is at most M over 4, 1/4 of the cache. Okay, that means a J funnel, which happens to have this size, fits in 1/4 of the cache. Okay, at some point in the recursion, we'll have this big tree of J funnels with all sorts of buffers in between them, and each of the J funnels will fit. So let's think about one of those J funnels. Suppose J is like square root of k, so this is the picture, because otherwise I have to draw a bigger one. So suppose this is a J funnel. It has a bunch of input buffers, has one output buffer. So we just want to think about how the J funnel executes. And for a long time, as long as these buffers are all full, this is just a merger. It's doing something recursively, but we don't really care. As soon as this whole thing swaps in, and actually I should be drawing this, as soon as the funnel, the output buffer, and the input buffer swap in other words, you bring all those blocks in, you can just merge, and you can go on your merry way merging until something empties or you fill the output. So let's analyze that. Suppose everything is in memory, because we know it fits. Okay, well, I have to be a little bit careful. The input buffers are actually pretty big in total size, because their total size is k to the 3/2 here versus k to the 1/2. Actually, this is of size k. Let me draw a general picture. We have a J funnel because otherwise the arithmetic is going to get messy. We have a J funnel. Its size is C times J squared, we're supposing. The number of inputs is J. And, well, the size of them is pretty big. Where did we define it? If we have a K funnel, the total input size is K cubed. So the total input size here would be J cubed. We can't afford to put all of that in cache. That's an extra factor of J. But we can afford 1 block per input. And for merging, that's all we need. I claim that I can fit the first block of each of these input arrays in cache at the same time, along with a J funnel. And so for that duration, as long as everything stays, all of that is in cache, this thing can merge at full speed, just like we were doing parallel scans. You use up all the blocks down here, and one of them empties, you go to the next block in the input buffer, and so on. Okay, just like the normal merge analysis of parallel arrays, at this point we assume that everything here is fitting in cache, so it's just like before. Of course, in fact, it's recursive, but we're analyzing it at this level. Okay, I need to prove that you can fit 1 block per input. It's not hard. It's just computation. And it's basically the way that these funnels were designed was so that you could fit 1 block per input buffer. And here's the argument. So the claim is you can also fit 1 memory block in the cache per input buffer. So this is in addition to 1 J funnel, you can also fit 1 block for each of its input buffers. Okay, this is of the J funnel. Not any funnel, because bigger funnels are way too big. Okay, so here's how we prove that. J squared is at most 1/4 m. That's what we assumed here. Actually, CJ squared. I'm not going to bother with the C, because that's going to make my life even harder. Okay, I think this is even a weaker constraint. So the size of our funnel proves about J squared. That's at most 1/4 of the cache. That implies that J, if we take square roots of both sides, is at most 1/2 square root of m. Okay? Okay. Also, we know that b is at most square root of m, because m is at least b squared. So we put these together, and we get J times b is at most 1/2 m. Okay? Now I claim that what we're asking for here is J times b, because in a J funnel, there are J input arrays, and so if you want 1 block each, that costs b, a space of b each. So for each input buffer, we have 1 block of size b, and the claim is that whole thing fits in half the cache. And we've only used 1/4 of the cache, so in total we use 3/4 of the cache, and that's all we'll use. Okay, so that's good news. We can also fit 1 more block for the output. That's a big a deal. So now, as long as this J funnel is running, if it's all in cache, all is well. What does that mean? Let me first analyze how long it takes for us to swap in this funnel. Okay, so how long does it take for us to read all the stuff in the J funnel and 1 block per input buffer? That's what it would take to get started. So this is swapping in a J funnel, which means reading the J funnel in its entirety and reading 1 block per input buffer. Okay, the cost of this swapping in is pretty natural. The size of the buffer divided by b, because that's just sort of a linear scan to read it in. And we need to read 1 block per buffer. These buffers could be all over the place because they're pretty big. So let's say we pay 1 memory transfer for each input buffer just to get started to read the first block. Okay? The claim is, and here we need to do some more arithmetic, this is at most J cubed over b. Okay? Why is it at most J cubed over b? Well, this was the first level at which things fit in cache. That means the next level bigger, which is j squared, which has size j to the 4th, should be bigger than cache. Otherwise, we would have stopped then. Okay, so this is just more arithmetic. You can either believe me or follow the arithmetic. We know that j to the 4th is at least m. So this means that, and we know that m is at least b squared. Therefore, j squared instead of j to the 4th, we take square root of both sides. J squared is at least b. Okay, so certainly j squared over b is at most j cubed over b. But also j is at most j cubed over b, because j squared is at least b. Okay, hopefully that should be clear. It's just algebra. Okay, so we're not going to use this bound because that's kind of complicated. We're just going to say, well, it costs j cubed over b to get swapped in. Now, why is j cubed over b a good thing? Because we know the total size of inputs to the j funnel is j cubed. So to read all of the inputs to the j funnel takes j cubed over b. So this is really just a linear extra cost to get the whole thing swapped in. Sounds good. To do the merging would also cost j cubed over b. So swap in costs j cubed over b. To merge all these j cubed elements, if they were all there in the inputs, it would take j cubed over b. Because once everything's there, you're merging at full speed. 1 per b items per memory transfer on average. Okay, the problem is you're going to swap out, as you may have imagined. As soon as one of your input buffers empties, let's say this one's almost gone, as soon as it empties, you're going to totally obliterate that funnel and swap in this one in order to merge all the stuff there and put it and fill this buffer back up. This is where the amortization comes in. And also, this is where the log factor comes in, because so far we've basically paid a linear cost. We're almost done. So we charge... Sorry, I'm jumping ahead of myself. So when an input buffer empties, we swap out. And we recursively fill that buffer. Okay, I'm going to assume that there's absolutely no reuse, that this recursive filling completely swaps everything out, and I have to start from scratch for this funnel. So when that happens, I fill this buffer, and then I come back and I say, well, I go swap it back in. So when the recursive call finishes, I swap back in. Okay, so I recursively fill, and then I swap back in. And the swapping back in costs j cubed over b. I'm going to charge that cost to the elements that just got filled. So this is an amortized charging argument. How many are there? Is the only question. It turns out things are really good. Like here for square root of k funnel, we have each buffer has size k to the 3/2. Okay, so this is a bit complicated. But I claim that the number of elements here that fill the buffer is j cubed. So if you have a j funnel, each of the input buffers has size j cubed. Should be correct if you work it out. So we're charging this j cubed over b cost to j cubed elements, which sounds like you're charging essentially 1 over b to each element. Sounds great. That means, so you're thinking overall, the number, I mean, you look at, there are n elements, and to each one you charge a 1 over b cost. That sounds like the total running time is n over b. It's a bit too fast for sorting. We lost the log factor. So what's going on is that we're actually charging to one element more than once. And this is something that we don't normally do. We've never done it in this class. But you can do it as long as you bound the number of times you charge. Okay? And whenever you do a charging argument, you say, well, this doesn't happen too many times because whenever this happens, this happens. You should say, you should prove that the thing that you're charging to, you don't charge to that thing very many times. So here I have a quantifiable thing I'm charging to, elements. So I'm saying for each element that happened to come into this buffer, I'm going to charge it a 1 over b cost. How many times does one element get charged? Well, each time it gets charged to, it's moved into a new buffer. How many buffers could it move through? Well, it's going up all the time. Merging always goes up. So we start here, and you go to the next buffer, and you go to the next buffer. The number of buffers you visit is log, it's the right log, it turns out. I don't know which log that is. So the number of charges of a 1 over b cost to each element is the number of buffers it visits, and that's a log factor. That's where we get an extra log factor in the running time. It is, so this is the number of levels of JFunnels that you can visit. So it's log k divided by log j, if I got it right. Okay? And we're almost done. Let's wrap up a bit. Just a little bit more arithmetic, unfortunately. So log k over log j. Now, j squared is like m, roughly. Might be square root of m. But log j is basically log m. There's some constants there. So the number of charges here is theta log k over log m. So now this is a bit, we haven't seen this in amortization necessarily, but we just need to count up the total amount of charging. All work gets charged to somebody. Okay, except we didn't charge the very initial swapping in everybody. But every time we do some swapping in, we charge it to someone. So how many times does everything get charged? Well, there are n elements. Each gets charged at a 1 over b cost. And the number of times it gets charged is this log k over log m. So therefore, the total cost is number of elements times a 1 over b times this log thing. Okay, it's actually plus k. We forgot about a plus k, but that's just to get started in the very beginning and start on all of the input lists. Okay? This is an amortization analysis to prove this bound. It's almost, oh sorry, what was n here? I assumed that I started out with k cubed elements at the bottom. The total number of elements in the bottom was k cubed theta. Okay, so I should have written k cubed, not n. This should be almost the same as this. Okay, but not quite. This is log base m of k. And if you do a little bit of arithmetic, this should be k cubed over b times log base m over b of k over b plus k. That's what I want to prove. Actually, there's a k cubed here instead of a k, but that's just a factor of 3. And this follows because we assume we're not in the base case, so k is at least m, which is at least b squared. And therefore, k over b is omega square root of k. Okay, so k over b is basically the same as k when you put it in a log. So here we have log base m. I turned it into log base m over b. That's even worse. Doesn't matter. And I have log of k. I replaced it with k over b. But k over b is basically square root of k. So in a log, that's just a factor of a half. Whew. So that concludes the analysis of a funnel. You get this crazy running time, which is basically sorting bound plus a little bit. We plug that into our funnel sort, and we get, magically, optimal, cache-oblivious sorting just in time. Tuesday is the final. The final is more in the style of quiz 1, so not too much creativity, mostly mastery of material. It covers everything. You don't have to worry about the details of funnel sort, but everything else. So it's like quiz 1, but for the entire class. It's 3 hours long, and good luck. It's been a pleasure having you, all the students. I'm sure Charles agrees, so thanks, everyone. It's a lot of fun.